Okay, students, let's go ahead and do our short lecture on Chapter 11, Equilibrium and Elasticity. All right. I don't know if any of you ever thought about it when you build a bridge, or here they're talking about an aqueduct. Of course, whenever you build a bridge, or whenever you build a house, or whenever you build anything that has any type of support on it, we would call it columns or legs. Of course, you know you do not want this object to move. You want it to be stationary. I mean, you don't want to drive across a bridge and that thing's bouncing up and down all the time, or swaying back and forth. No, we don't want that, do we? Well, we do know that even rigid objects have a tendency to move a little bit, don't they? They are not truly rigid. They are actually a little bit elastic to some extent. So, that being said, then we have to take into consideration how to build bridges and crosswalks and buildings so that they will stand up and not collapse. So we have to look at something called conditions for equilibrium, and there's actually two that must always be satisfied in order for a building or a bridge or any object that has something suspended on it to stay at equilibrium. In other words, not come falling and collapsing down, okay? So, of course, the first condition has to be that all the vector sum of all the external forces acting on the body should be equal to zero. Now, that's really Newton's second law. If you go back and remember when we talked about Newton's second law and we were calculating forces, remember we'd always say, well, if the object's not accelerating, then the sum of all the forces is equal to zero. Well, that's what you want. You don't want that bridge accelerating. You don't want that bridge span bouncing up and down. You don't want it accelerating, okay? Or it'll be like the Tacoma Narrows Bridge. It'll come all to pieces, won't it, okay? And then, of course, the second condition is that the sum of all the external torques must be zero about any point, okay? You've got to keep the torques, the sum of the torques now. The sum of the torques. Doesn't mean there's not torque. It's just that the sum of the torques have to be zero about any given particular point, okay? Because torque, if you have external torque, then guess what? You're going to either cause rotation or stop rotation, okay? In other words, there's going to be motion if there's an external torque, and we don't want that with a bridge, do we? No. All right, so here's a condition. This is an example they show. This is in your book on page 340. On page, I do it every time, page 340. You see, this is on page 340. You see this situation here. Notice that both of the forces are in the same direction. Okay, notice that. So the sum of the torques is what? Well, notice that since the forces are both in the same direction, okay, notice you have your axis of rotation. You have a force that's perpendicular. Notice you got 2F here and 2F. You got 1F going up and 1F going up. That would come to 2. Then guess what? There would be no net torque. Because why? Because the sum of the torques are equal to zero. You also see that the net forces would equal zero also, because why? You've got two forces here, you've got two forces here, then guess what? There's no rotation going to occur, okay? All right, that's condition one. However, we look at condition two, example two, this tendency has no tendency to accelerate as a whole, but it does have a tendency to start rotating, because look, you say why? Well, because notice you've got a torque up, you got a force up. And remember, how do we calculate torque? Well, the torque, remember, if you go back and look at your equations, and I believe it was what, chapter 10? Yeah, the force times the length, FL, is torque, isn't it? Well, notice that one is going up and one is going down, all right? So the first condition as far as the body at rest, that is the net forces are zero. I mean, if you think about it, you got forces in opposite directions, so the net force would be, this force would be positive, that force would be negative. Looks like the vector's the same, so it'll be zero. However, you have a net clockwise torque about the axis, so the body will start rotating clockwise, okay? Because look, this is going up, this one is going down. You add the torques together, and guess what? You get rotation, don't you? All right, but now let's look at this one. This one's kind of odd, isn't it? This body has a tendency to accelerate, but it doesn't have a tendency to start rotating, okay? Well, look, First of all, the first condition is not satisfied. There is a net upward force. You say, well, what do you mean? Well, look, you've got 2F here, and then you got F over here. All right? Notice they're both going in the same direction. All right? Notice both of the forces are up. So you don't have equal forces, do you? There's no force counteracting here. So you would have a net force, wouldn't you? So that would cause it to start moving upward, or it to cause it to start turning, wouldn't it? Or accelerating, excuse me. If you have net forces, then guess what? If there's net forces, then you've got acceleration, don't you? Okay, remember? You say, how do you get that? Where do you get that? Okay, look, sum of all forces is equal to ma. All right, look, if there's a net force over here, you're going to have acceleration. However, the net torque about the axis is 0. You say, well, now how in the heck did you get that? All right, look, take this right here and calculate the torque, and take that side there and calculate the torque, and you'll see that there it will equal 0. Okay, it will equal 0. All right, because this one is going, look, this one is going that way, and this one is going that way. They cancel each other out. Okay, so there's no tendency for it to start rotating. All right. Now, in order to understand elasticity and equilibrium, we also need to understand something called center of gravity of a rigid body. The center of gravity tells you here is the point at which all the Earth's gravity is centered at, based on the shape and size of the object. Okay. All right, so notice you have, and they're showing you here, talking about the different torques and everything, and of course we know that weight is equal to the total mass times g. Now, you say, well, how do we determine the center of gravity? Well, again, you have to find the axis of rotation, okay? And of course that will be based on how much torque you have on each side of the axis. So center of gravity, and of course it says we can treat a body's weight as though it all acts at a single point, the center of gravity, okay? And every object on the earth has a center of gravity. Here they talk about the acceleration due to gravity at the bottom of the 452 tall Petronas Towers in Malaysia is only about what? 14 thousandths greater than that at the top. Okay, so the center of gravity of the towers is only about what? 2 centimeters below its center of mass. So that's really close, isn't it? Sure is. All right. Okay, so center of gravity. Here they give you a couple of examples here. And you say, how do we know to find the center of gravity? Well, notice right here, if you grab the handle of this coffee cup right here and let it dangle, all right, then your center of gravity has to be here. But if you move your fingers up on the handle, then notice how the center of gravity you've got, because look, here is where you have a hold of the handle. All right, here is where the handle is connected on the other side. So notice right there is your center of gravity. So notice how the center of gravity shifts just by slightly moving your fingers up on the handle. Notice that you didn't move them very far. Notice how it shifts the center of gravity. Okay? All right, hope that makes sense. Okay, now, why is this important? Well, folks, you have to think about especially when you're looking at objects in motion on a track or on a road or on a bridge or on a highway going through the mountains, and if you've ever traveled much, you've noticed that when you go through curves, or especially roads through mountains, they have to wind the road to get it up the hill, don't they? Typically, okay? And in order to do that, they have to bank the curves, don't they? Well, if you've ever noticed, most of the time the curves that you see in mountain passes, or even on a regular typical road just out on the flat ground, if you go through a curve, you notice that they try not to bank it too much. And if the reason being is because if you get the center of gravity beyond the actual width or beyond the actual object, guess what will happen? All right. Notice if you go with a higher slope, notice that the center of gravity is outside the area of support. Okay. So see, look right here. Here it's within the area of support. And you say, where's my area of support? Well, look, it's right here, isn't it? It's right here. Right there. In other words, between the wheels. But here it gets beyond the center of support. So notice my center of gravity now. Notice, look, it's outside. It's outside. And so guess what's going to happen to the car or the truck? It's going to tip over. And so we're not at equilibrium, all right? We're not at equilibrium. So problem-solving strategy, again, for static equilibrium. Of course, again, this does not really change that much. You always have to sketch it. You have to draw your free body diagram, choose your coordinate axis, choose a reference point, and then the same thing as follows for solutions. You write your equations. The sum of all the forces is equal to 0, in the F, X, and X, Y, and Z directions. Of course, same thing with torque. And then, of course, you use whatever equations you need to solve it. All right. Now let's look at stress and elastic moduli. There's actually 3 types of stress, and some of you may have already known this. You have tensile stress. If you've ever used a rope, you've ever used a cable, tightening guitar strings, banjo strings, mandolin strings, whatever, piano strings, that is tensile stress, okay? If you look at an object underwater, you have what is called bulk stress, okay? Bulk stress, all right, because the object is receiving stress on all sides. And then you have something called shear stress, like cutting paper, cutting ribbon, cutting a piece of steel, cutting, paper with scissors, whatever, okay? So there's 3 types, tensile, bulk, and shear stress, okay? So what is stress and strain? All right, when you apply a pressure, when you put force per unit area, that's called pressure. That is referred to as stress. But however, when you change the size of your nose here, as they say, pinching your nose, you do what's something called strain, okay? So applying pressure is stress, and changing the size is called strain, okay? Does that make sense? Okay, if you take a piece of metal and you hit it with a hammer, you apply pressure when you strike it with a hammer, and if you deform the metal, then that's called straining the metal. And the deformation is due to elasticity. Now, some objects are much more elastic than others. I think that's that's one of those commonsensical things that that say a piece of rubber or a piece of plastic typically is much more elastic than, say, glass or a metal. Now, some metals are elastic. Softer metals typically are. They're more what we call malleable. But typically, metals are fairly rigid, especially if it's iron or tungsten or something like vanadium, chromium, okay? So let's look at tensile stress and strain. All right, so to calculate tensile stress, then we look at the force per unit area. And by the way, that is the force applied perpendicularly. That's how we calculate. Here's you some more equations for your formula sheet. The force applied perpendicular to an area is called tensile stress. Tensile strain is the change in the length over the initial length. That L sub naught is initial length. That is the initial length. This is called area. And of course that is perpendicular force applied perpendicularly. That is initial length. Okay. And that's the change in length. I ought not have to write that. You ought to know that delta is change in length, okay, or change in anything, okay? So that's how we calculate tensile stress and tensile strain. Then we can look at something called Young's modulus. So when we look at the ratios, or when we compare the tensile stress of an object to its tensile strain, basically what are we doing? What is Young's modulus? It's just a ratio of those two, tensile stress to tensile strain. So Y, Young's modulus, is equal to what? The force, perpendicular force per unit area divided by the change in length divided by the initial length, or we can write it this way. We can say the perpendicular force per unit area times the initial length over the changing length, okay, what we call elongation, and we can find Young's modulus that way, okay? So now let's look at compressive stress and strain, and we should have a table here that shows us gives us the values of Young's modulus. On page 349, okay? So now that was tensile stress and strain. What about compressive stress and strain? Notice it's basically the same thing, isn't it? It sure is. So compressive stress and strain. So we have stretching and compressing. So compressive stress, okay, look at there. The perpendicular force per area, and compressive strain, the change in length per initial length, okay? It's the same calculation, isn't it? And you say, well, why would this be important to know? Well, look, if you take a beam, and notice it's supported here at the ends by columns or rods or whatever, notice the top of the beam is under compression and the bottom of the beam is under tension. So, boy, you really got to know your material here, because it's going to change from one side to the other. Okay, the top of the beam undergoes compression. The center, there's none, but the bottom of the beam undergoes tension, doesn't it? Isn't that crazy? I don't know if you've ever thought about that, but that makes a lot of sense. Okay, if you've got cars going across this up here, then these are under compression, and then you're going to have a lot more tensional strain underneath. So, to find what we call bulk press and stress and strain, now most of you probably know how to calculate pressure, and that's lowercase p, pressure. This is pressure, that stands for pressure, and you know that's force. And this is area, okay? That is area. So the force applied perpendicularly per unit area is something called what? It is called pressure. And by the way, the units for pressure are PA. And by the way, I should have mentioned this. The units for Young's, where's it at? The units for Young's modulus is, the units are PA. If you do all the math, you find it to be what? You find it to be pascals, okay? So really we're looking at pressure, okay? See that right there? They give you that for the human tendon, but notice the unit there is PA, that is pascals, okay? Pascals. All right, so then force is the, pressure is the force per unit area, okay? Very simply calculated. But what about bulk modulus? Bulk modulus. Now remember we talked about tensile, we talked about bulk, and then we talked about shear. All right, let's look at bulk's modulus. Bulk's modulus is what? It is the change in pressure. Notice this right here, and it's the negative change in pressure. It's the negative change in pressure. All right, times the what? The change in volume. That's change in volume. Over what? The initial volume. Okay. So we can find then bulk modulus simply by taking the change in pressure and multiplying it by the ratio of the changing volume over the initial volume. Okay. Very simple calculation there. And that negative sign, y'all, is very, very important. Okay. Very, very important. Because what if the pressure decreases? If the pressure decreases, if the change in P is negative, then it's negative times negative, which is positive. So your bulk's modulus would be positive, wouldn't it? Now, how do we find bulk stress and bulk strain? Well, looky there. Bulk stress is the change in pressure. Bulk strain is the ratio of the changing volume to the initial volume, right? It's just a ratio, okay? So it's important that you have those equations. All right. Now what about shear stress and shear strain? Shear stress, we've talked about tensile, we've talked about bulk, now let's talk about shear. Well, shear stress, now notice this right here. We're looking at forces that are what? Parallel to each other. So basically it's what? It's the shear stress S, and again y'all, units are still going to be what? PA? Yeah, it's going to be PA. By the way, the units for all of these, I hope you caught that. The units are PA. Pascals. All three of them. And you can see this on page 349. Page 349 on the table for Young's bulk and shear modulus. Okay? Now, so if you take then the shear stress, which is what? Notice it's the same thing, y'all. Look, that is pressure. Force per unit area. It's parallel forces, though. This is parallel forces. Oh, I hope I spelled parallel force, okay? Parallel forces divided by the area times the height divided by what? Divided by x. So the height of the area of the object divided by what? The width of the object. Okay? You see this right here? So shear stress is the parallel force divided by the area, and shear strain is the x, the width, divided by the height. Okay? All right? That'd be like the width of the blade divided by the height of the blade if it was scissors. Okay? And again, the units are PA. And there's your values. Okay? That's on page, what did I say? Page 349. Yeah, 349. Yeah. Okay? All right. Okay. And by the way, on your midterm and final, I will do my best to have you a formula, your constant sheet that'll have all these bulks, Young's, shear modulus, and everything on it. Okay. All right, and that's where we're going to stop. Okay. Oh no, excuse me. I don't need to stop yet. I don't need to stop. I'm sorry, I forgot about compressibility. Ooh, about to forget about that. Now, compressibility is basically what? It's the reciprocal of bulk's modulus. And notice that our units change a little bit. Change just a little bit. I almost forgot about this, y'all. I'm sorry. That it's reciprocal pascals or atmospheres. Typically, we do everything in pascals. In other words, it's 1 over Pascal. That's our units, okay? So if we look at the compressibility of, say, a liquid, and notice these are all liquids. These are all liquids. Then it's basically the reciprocal of what? Of bulk's modulus, okay? Now, what about elasticity and plasticity? All right, when we're looking at Hooke's law, and of course, when you look at Hooke's law is a direct proportional relationship between the force applied, or the restoring force, with respect to the change in displacement from the equilibrium position, isn't it? Okay. Now, as long as we stay in a linear region, then we what? We are fulfilling Hooke's law, and there's no change in the amount of force applied, right? However, notice that the graph begins to curve. Notice that the stress-strain curve for increasing stress. In other words, notice that stress is decreasing, but strain is increasing. Notice right here, stress is increasing, but strain is decreasing, okay? So what does this tell us? This is showing us the typical stress-strain diagram for vulcanized rubber, okay? And it's illustrating something called elastic hystasis, or hystasis. In other words, the elasticity of an object. Now, you can actually calculate this. If you were to take some rubber bands, you can take the rubber bands and stretch them, measure their initial length, and then stretch them, and then let them return back to their equilibrium position. And notice that the difference in the rubber bands before stretching and after stretching is different. It will not be the same, and that is called rhistasis, okay? Elastic rhistasis. And basically that change is the rhistasis. The change in length is the rhistasis of the rubber. And what does that mean? Well, eventually it's going to do what? You keep stretching it and stretching it and stretching it and letting it go back and stretch it and let it go back to equilibrium, stretch it and let it go back to equilibrium. It's eventually going to break, okay? And so you can determine the life of a piece of rubber or any material by looking at rhistasis, okay? Okay. And again, this is the same thing, looking at the elastic limit. This is for a piece of metal. Notice right here, we've got a nice linear relationship. Everything's okay. But when it starts to do this, we get what is called plastic deformation. Okay? All right? Plastic deformation. In other words, it's being stretched, and then here, when it starts going down, you get to what's called the fracture point. So in other words, what is this telling us? All right, look, right here we're good. We're good. All right. we're within the elastic limit or yield point of less than 1%. So we're doing pretty good. But once we get beyond point A, and especially point C, B, and C, this is where we don't want to get. All right, you don't want the metal on that bridge to stretch. Okay, you want it to flex but not stretch. Okay, and boy, here's where it becomes detrimental. You keep stretching it, you eventually get it to the fracture point. The steel cracks and breaks and you have a bridge collapse. You don't want that. You want it to stay right here. You want it to obey Hooke's law. You want it to stay right there. All right. You want it to stay at equilibrium. It's okay to flex a little bit. Okay. But you don't want to stretch it. Flex but not stretch. Okay. All right. I hope this helps.